I'm the reporter from Team Taiwan. Now I'm going to report on number 10, the standard water wheel. This is form statement. Carefully place a light object, such as styrofoam disc near the edge of the water jet aiming upward. Under certain conditions, the light object will be spin while being suspended. Measure this phenomenon in stability and external situations. So the reporter will mainly focuses on what causes the light object to be suspended, the parameter that influences phenomenon, and also its stability under external situations. So this will be my presentation outline. First, I will give a preliminary experiment showing up by showing you an observation video. In the third part, I will be talking about the corona effect and the force analysis that act on the light object. And the next part, I will be talking about the experiment parameter, which will be about the radius of the weight of this cross area of the water jet, and also the flow velocity of the jet, and also we will be discussing about the stability of this. And that's will be my conclusion. So first, this is the observation. So this is an observation of video of this phenomenon. So you can see we place a light object on the water jet on this, it will start to rotate and will be suspended. So you can see in this slow motion video, you can see that the water jet will actually go around this and it will be splashed out at the same time. So in the theory part, we'll be firstly talking about the corona effect and also the force analysis. So firstly about the corona effect. While you are placing a water jet aiming upward, it will look like this. But when you are placing the light object that's close to the water jet has a tendency that the water jet will go around this. And so this will be due to the viscosity force that act on the between the light object and also the water jet. And this will cause the pressure gradient, and this will cause the water jet to will be affected by the curve of the light object. So this will be the force analysis that acts on the light object. So first there will be an impulsive force that acts on the water jet. So this will be impulsive force that acts on this direction. And also there will be a reaction force of the centrifugal force that firstly the light object will give a water a centrifugal force that causes the water to go in this direction. And also the water will give a reaction force of this centrifugal force that will act on this direction. So by this force, the combination of this force will compared to gravity, this will cause the light object to be suspended. So here will be the basic assumption of this theory. So first we consider water motion as the projectile motion, and also we have a simple approximation that the water will hit this at the angle negative theta, and that at the angle theta. So this will be so by this simple approximation, this will cause the calculation to be more easier. So first we will be analyzing the forces on the z-axis. So first we will be at the F1 will be the impulsive force that caused by the water jet, and also the F2 of the reaction force that caused by the centrifugal force. So because we assume that the water jet will hit on the angle theta and that's on the angle negative theta. So by this assumption that the direction of the F2 will point in this direction. So we can analyze this with the axis. We can get that this will have a water jet maintained at the same angle theta. And also, so by the previous calculation, we get when we are analyzing the forces that act on the z-axis, which we can get when the z component of the forces will be equal to the gravity of it. So we can get the velocity of the tangential velocity of this will be rotating, and also the height of it. So the tangential velocity it will be rotating will be affected by will be equal to 1 over sin theta times the square root of the mg over log a. So this will be affected by the sin theta, which will be affected by the heating angle, and also the weight of it and the cross area. And the height will be affected by the initial velocity of the water jet, the heating angle, the cross area, and also the weight of it. So also we'll be discussing about whether under external perturbations that when they rotate with delta theta, we assume that when it's very little, it will have a distance that we move will be defined as an x. So here you can see when it's very small, you can get this equation, and where the delta theta will equals to about the x over L times theta. So by this two equations, we can analyze the axis force that act on the x-axis, we can get the k constant will be. So the light object will have a motion like a simple harmonic motion. And so by this, the k constant we can get the annualized by the stability of it, the stability will be affected by the area, the initial velocity, heating angle, and also the radius of the disk. So about the experimentation, we'll be first thinking about the equipment and setup, the investigation of the parameter is homogeneous motion, and also its stability. So this is the equipment that we use. We use a standing roll disk and use the pipette. The pipette is used to control the cross area of the water jets. So this will be an experimental setup. The pipette will be connected with the pipe in the faucet, and here's a picture of the pipette that we use. So here will be a parameters that we use in this experiment. First, we'll be talking about radius of the disk and also the weight of the disk, and about the cross-section area of the water jet, the flow velocity of this will analyze its stability. So this is the radius that we use will be from 2.65 centimeter to 4.85 centimeter. We all control the same weight of 1.2 gram. So this is the describes the relationship between the radius and the heating angle. So you can see when the radius of this will be getting bigger, the heating angle becoming smaller. So this will guess when it is when the water jet hits the same when it is suspending the same weight of the light object, it will hit the same position of the light object. But because when the radius will become bigger, so it causes the heating angle to become smaller to hit at the same position. So by the measurement of the heating angle, we can get the calculation of the theory of the height of this. So you can see when the radius of this will get bigger, the height of this will get smaller. So this will because when the radius of this, so according to the theory, we can get the theory relationship between the radius of this and also the height of this. So the deviation here I believe will be caused by the approximation that we assume that will be heat at the angle negative theta and give us the angle of theta. And also this will be affected by the radius of this. And then we can compare to the height of this, the height of the light object and the angular tangential velocity of this. So here we choose to analyze the tangential velocity, which is because the radius of each disk will be different. So we analyze the tangential velocity of the disk. So when the radius of the disk will get bigger, the tangential velocity becomes bigger. So this will be due to the height of the height of what is what being suspended. So because of the suspended position becomes smaller, the tangential velocity of the light disk will become bigger. So here we'll be talking about the relationship between the weight and the heating position. So when we are fixing the same radius of both but with different rates, the heating angle will become bigger. With a bigger heating angle, that will be the water jet will heating this with the closer to the center of this to support the bigger weight of the disk. And also you can see that when the weight of the light object will become bigger, the height of it becomes smaller. And also this will be compared to the theory of this. And when the stopping position of it becomes smaller, so it causes the angular velocity become bigger. So here we use the angular velocity because the radius of it will be the same. So we only calculated the angular velocity of it. And here will be an experiment about changing the cross area and we control this of the raise the weight of it. And we control the height of the water will be maintained by the control of the flow velocity of it. And we only change the cross area. So here you can see when we are lifting the same disk of the heating angle won't be affected by the cross area of this. But the same cross area of it will be only affected by the area cross section area. So here you can see when the cross area will become bigger, the stopping position of it will become bigger. And also you can see that the deviation between the theory and the experiment becomes smaller when the cross area is becomes smaller due to the just I mentioned the simple approximation of the theory. And here you can see when the also I mentioned when the stopping position of the light object becomes smaller, so it causes the angular velocity of the light object become bigger. Now here we control the flow velocity of it with the same cross area and the same disk. So here you can see the black dot will be representing the height of the water, and the red dot will be representing the height of the disk. So you can see that when we are placing the same disk on the water jet, it will cause the same distance change in each flow velocity. And also the height of the water will be representing the tangential velocity of the flow velocity, the tangential velocity of the light disk. So when the height of this will become bigger, also the angular velocity becomes smaller. And here we'll be analyzing the period of the simple harmonic version of the so you can see so this will be the y here will be the center of the ideology. So this will be a top view that when the watch is aiming upward, we film it like this. So this here will be the y position with the with the time. So you can see here will be a periodic function, and we analyze the period of this. So here will be we calculated the r over the sin theta, the square root of r over sin theta. So you can see we got the linear relationship between the so you can see the radius of the and the period will be affected by the heating coefficient and the radius of it. So we can get a linear relationship between the r over the sin theta. And also here we'll be changing the cross-section area, and we also in our experiment we control the sin theta and the cross-section area, and there will be also the linear relationship between the cross-section area and also the period of it. Here will be we're changing the weight of it, and will be so there will be a square root of the m over sin theta we compare to a period, and also there will be a linear relationship. And here will be the experiment about the stability of it. We use the air compressor, we will close the air to the height of the disk, and we control the distance with 9 centimeters. So in this experiment with the authorities over the certain point that the object will fall down, and we control the different height of this will be affected by the different flow velocity of it. So you can see with the flow velocity of it will be more stable on the water jets. So this will be my conclusion. The second one, this will be affected by the repulsive force and also the reaction will caused by the Coulomb effect. The radius of the weight and also the cross area of the origin will affect the height, the angular velocity, heating angle, and also the period of it. And the height of this water will be
Sorry
more
to
stable.
interrupt you there. 2 minutes time for the opponent to ask questions.
So let's first discuss how did you measure the velocity of the tangential velocity of the water?
We'll measure the omega of it, and we'll times the radius of it.
Okay, so in slide 20 to 19, how were the theory points determined?
Sorry?
Actually, that's all right. How did you change the weight? Did you keep the radius the same?
Yes.
So did you vary the
We
density?
will average in the center of the thermal disk.
Did that change the moment of inertia?
Yes, it will change the moment of inertia.
So how did you define the water jet in your system?
Sorry?
How did you define the water jet? Stated in the problem statement as water jet.
The water jet?
Was the water jet laminar, transitional, or turbulent?
Laminar.
Laminar. Are you sure?
Okay,
Okay, that's fine. So did you test other surfaces of the disk? So,
But this, if the surface
That's
is
fine.
smoother, it will be better.
yeah, did you take limits of the mass on when this did and didn't work? So
we-
too much mass won't suspend and too less mass. The limits of the mass of
I
the.
think there will be a limit on the mass. When the
Okay, that's fine, thank
become
you.
bigger, so it will be GP to be suspended.
What was it? Do you have any limits on the jet velocity? And then when there's too much velocity such that it doesn't suspend?
I know.
No. Okay. Was there what assumptions did you make to model the wheel? Were there any assumptions you made to model the wheel?
Not on the wheel.
No. Did you take into account the droplets of water that flew off the wheel?
No.
Did you account did you account for the momentum of the wheel?
Sorry?
Did you account for the angular momentum of the wheel when discussing stability?
Yeah. It's also because of the radius of
Alright, that's fine. Did you have a quantitative explanation for why the wheel is suspended? Like why it's stable?
Okay, sorry. There's one more time for an answer, and please proceed to preparation. Please start the opposition.
So are we proposing quantitative suspended water wheel? So I'll be, as I know my presentation, I'll be going over the overall presentation, the theory outline, the experimental, the results, and points of discussion that I'd like to bring up. So the problem statement states, carefully place a light object such as a styrofoam disc near the edge of a water jet aiming upward. Under certain conditions, the object will start to spin while being suspended. Investigate this phenomenon and its stability to external perturbation. First thing I'd like to state is the reporter lacked to actually establish certain conditions on in the system, and I'd like to move on and discuss a bit more. So the fairness in the theory, the reporter is able to use the Iguana effect to describe the curvature of water around the disk, which is a valid way, model of describing the situation. And they used an effective mathematical model to describe the nature of the wheel and the properties and how it worked. However, I thought there were some things to areas of improvement. So assume the water would totally stick onto the suspended water wheel, but that they did not consider the water droplets or anything else. So the quantum effect doesn't explicitly say all fluid will stick around the surface. There's an extent and a limit to this situation. The problem statement explicitly states that spinning. However, in the solutions to the mathematical model, angular dynamics was not taken into account. They are later brought up in the results, but they're not explicitly taken into account, whereas they use translational mechanics and tangential velocities rather than some of the angular properties of the disk. And in theory, did not discuss the flow type, either as laminar, transitional, or turbulent, and that actually plays a part in the force of the actual jet on the disk. And the cross-sectional area was also an approximation used, but in fact the cross-sectional area of the contact is not in fact a circle. So also the theory also discussed harmonic motion and the quality and modeling the wheel as a harmonic oscillator. However, going back, the flow is absolutely not a laminar flow, as shown in their own videos and support. So they said it was laminar flow. However, their own experimental results denies this. And the problem states that certain conditions for the problem works, and they're non-stated. There are no statement of certain conditions which this problem works, and that relates back to problem fulfillment and why there's some flaws in that. So the variables were tested, such as radius, weight of the disk, and as well as cross-sectional area and flow of the jet, which is a good spread of results. However, there are no limits of the mass of when the phenomenon occurs, so there's no limits taken once again, or the radius. And is there a point where it stopped working for the same jet properties? And that's something I'd like to bring into the discussion. So some main ideas to bring into discussion is, what is the intuitive explanation to the phenomenon using basic physics principles? I think the reporter lacked the ability to explain this intuitively in a really simple physics sense. And also, I'd like to bring in, how does the quality of flow affect the situation? Do some of the approximations using the force rho v squared only apply to laminar, turbulent, or transitional flow? And the reporter lacked the ability to explain a large situation and problem, which is the stability of the situation, external perturbations. There were no quantitative explanation to how much these perturbations were, and that's why I'd like to discuss how the stability is achieved. Is it through angular momentum conservation, or is it through some force balancing? That's what I believe the reporter lacked, and I'd like to bring up in my discussion on how these properties do affect the situation. So I believe the problem wasn't fulfilled to its fullest extent, as the problem stated. External perturbations and stability was a big key, but the reporter lacked to explain these quantitatively and also qualitatively. And I'd like to bring that up and discuss some of the limits and conditions of the experiment. So I'd like to start discussing. So I'd first like to ask you, so you said the flow was laminar, is that true?
Yes.
Can you please send to the video of your, your slow motion video?
So I think it's an explanation of this video because so you can
play the video,
see as the water jet of water will be splashing away. So no one's waiting his.
No, but I understand that. Why is there space in
this is a
the
drop observation video. In all of the experiments, they will not be in this for initial flow velocity.
Did you take any calculations such as the Reynolds numbers or anything to at least give you some quantitative backing to why this is laminar flow?
I don't think that the laminar flow or turbulence that will affect this the force that act on the.
Did you? But then when I saw you use the rho v squared as an assumption, that assumes constant mass flow rate, and that includes laminar flow. I saw
you calculated by the flow rate of it.
The flow, yes, but that rho v squared comes
and we have factored when it is the laminar flow and turbulence, so I found that it doesn't matter.
Okay, so I believe something like this. You need to use some you need quantitative backing to why this you can conclude is laminar flow.
Okay, but I believe that this that's backed by our experimental results. You have factored it.
Okay, then let's see. So one something you didn't discuss the limitations of your model.
Yes.
So you vary the density. You vary the density by changing the internal mass of the system. Yes.
The density of the water was density of the.
No, sorry, the distance.
But that in the theory part, the density will be about the density of the liquid. and we are only using.
So is the styrofoam the same density as the liquid?
No. The density in our theory, we only talking about the density of the. I don't think that density of this will affect this phenomenon.
No, but then how did you vary the mass without changing the radius?
We
If
add
the
mass to
density
the
is
center of it.
So how, wouldn't that change the moment of inertia of all this?
And you will change the moment on the result.
Then wouldn't that affect your result?
Yeah, yes, of course. We're discussing about the effect of that in our
No,
experiment.
say if you increase the moment of inertia, if you increase the mass in the center, that would change the moment of inertia. So when you use some of these approximations, these include a moment, the equally distributed mass. So a lot of your graphs should technically have a different, the angular velocity shouldn't match your theoretical. Then why do you think some of your theoretical values work with the experimental?
Sorry?
The moment of inertia of your mass changes, yes?
Yes.
Yes,
but-
you acknowledge that?
We add in the
But
center
your
of the
equations
result.
use the assumption that there's an equally distributed mass in the disk, yes? But that is not the case, of course, you've admitted that.
With the force of the angular would be add on the center of mass, on the center of the disk, and we add a mass on the center of the disk.
Okay, then, I don't agree with that, but I will move on from there. So you didn't test the different surfaces, yes? You just tested them. How do you think the surface would affect the situation?
In our experiment with the styrofoam disk has a for example, and with the styrofoam, can we write down this? Sorry, check.
You can just run it, but.
So in the styrofoam disk that there will be a non-released surface that will cause that object just fell of the water depth.
Okay, so say if I reduce the frictional coefficient of the surface by either taping it up, how do you think that would affect the system?
I believe it will rotate faster and the potential of it will become bigger.
Okay, yes, I do agree with that. That makes sense, yes. So I'd like to go back to external perturbations. Did you quantify how much you're disrupting the system? How did you, the problem statement explicitly asks its ability to stay stable against external perturbations. How did you quantify your external perturbations, if you did at all?
So we use the K constant, so because this will be a simple harmonic function, so for example,
No, I'm talking about the external perturbation. So this is stability, your thing is stable. The problem statement explicitly asks.
So by using air compressor that will close air to the.
Did you quantitatively measure this?
Yes, we use the flow rate to exchange.
Okay, so which side of the disk did you put this on? Like, did you put it on this side, or how did you shoot this on the
We shoot for example, this is the data will flow in this direction.
Did you try the other direction? Or this way?
As our triangle has a similar result, but not the exact value, but the same tendency.
Okay, so in that case, I'm going to ask you a question, sorry. In regards to external perturbations, because you didn't explain a lot of the physics behind it, do you think angular momentum is conserved for the disk while it is suspended?
The angular momentum.
Yes, of the disk is
I
conserved.
don't know. We have just a water that will act on the
Wait, does the angular velocity of the disk eventually stay constant?
Yes.
Yes, that means angular momentum is conserved.
So
Angular
this will
momentum
be
is equal
affected by
to the moment of
resistance
inertia
force.
times the angular velocity, yes?
Yes, because
That means
we
it's
have
conserved
the
in a stable
distortion
situation.
and also the water depth of it.
No, but if the angular velocity is constant, the moment of inertia is constant for a given disk, angular momentum is
Oh,
constant.
that's
So I
the
want
result.
I want to give you a situation then. We know angular momentum is conserved. So say if I have a 3D disk here, and it has some angular momentum, and because it's rotating this way. So say if I apply, say your stability in this experiment, you apply some force this way, what would happen
No,
to this?
in this way.
Yes, I want to take this situation. Because this is part of the problem statement. The problem statement is external perturbation. I understand you put some force this way, but what about the wobbling motion? What would happen if I put a force this way on the top? So I maybe even tapping it or maybe applying some force. How would this system stabilize itself? Because that's part of the statement.
I believe this perturbation will be big enough that it will be just this will be just of the water depth, and I believe when they have the small enough because of the corona effect. So and here is the water depth that.
Yeah. No, but we're in a situation where angular momentum is constant. This is in stable configuration. And the problem statement asks how external perturbations, such as just some force, any force, acting on the disk.
Yeah, so if the force that acting this way, this will cause it that the water only hit the half of the
So what's the tendency for the system? So say if I push here, what would happen?
If the force is one value, it will move back.
It will move back in which direction? Can you show me using angular momentum? Can you show me some of the torques involved in the situation?
So, here's a water jet. And you shoot this way, and then look.
Okay, I'll show you. This is what I think happens in this situation. So there's a radius vector here, and this cross here. So we already know torque is the cross between radius and force. You know this, you are aware of this?
Yes.
Yes, so if I apply force this way, it results in a torque into the page, and that results, if you use your right hand rule, it results in this twisting, like this, yes. And that results in an angular momentum change here, and the system wants to oppose this angular momentum. So out of the page, there's another change, a negative DL, results in a torque in the opposite direction. And this results in a stability like this. I think this is extremely important.
I think in this explanation, you didn't consider of the change of the water jet. Because of when you place a force here, like the water jet hitting the area.
I agree with you, but the only reason the system is able to go back is because of the distribution of the water jet. There's another force acting that creates this opposite torque. So I agree with that, but you're unable to actually describe why the system does it.
Just telling you that this is because of the dissipation of the water jet.
No, but that comes back to the problem statement. It says discussing the stability of the system, and I think we lack in that section as well.
In this situation, we're just talking about this thing.
Okay, sure.
We're just talking in different direction of the flow air of the external fluctuations.
So we can go back to your video, please. Your video of the thing. So you talk about the water jet, but it's obviously in your system, your disk is wobbling.
Yeah, so we have we're talking about this will be a single harmonic motion we have measured. Yeah, so this will be the observation video. Yeah, so you can see that the wobbling you have in the theory, we have calculated in the single harmonic motion. You have the.
But you didn't take wobbling in this direction, yes?
I believe that we have measured in this direction. I believe that this will be a state.
Yeah,
the
that's fine.
of this will be a.
But I guess the problem asks certain conditions. Did you find certain conditions for which this didn't and didn't work?
Does it will not be suspended?
Yeah, but all the conditions of suspension is extremely key.
If the weight is too much or something like that.
Did you put in quantitative or qualitative reasoning?
We cannot measure the.
So you're saying you didn't fulfill the problem completely?
I believe that, we have also. I didn't have.
Because two of the statements talk about external perturbation and stability, which you obviously did not show using physics or qualitative observation, and also certain
We'll
conditions.
be talking about in the theory that the weight of in our theory and predict that when of the weight cannot be suspended, like for example, like the weight across area and the initial velocity. So in our theory we can predict it.
Okay, that's interesting. But so you're also discussing cross-sectional area. The cross-sectional area of this jet is not the same as the cross-sectional area here. It's this curvature of the surface, so it involves the surface integral.
Because of the curvature will be like the.
Okay, that's fine.
The cross-section area actually will be proportional.
Okay, that's fine. So in general, you were unable to actually show the certain conditions with some of the limits.
We can measure it.
No, the limits of your model, you're unable to show some of them. Yes.
Okay, but I'll ask your opponent to summarize the discussion.
So the problem statement explicitly asked to investigate a water jet aiming upwards, and the problem explicitly said under certain conditions the object will start to spin while being suspended, and the question asks us to investigate external perturbations and stability. As seen by the reporter, they're unable to actually provide any certain conditions for why the system stays on. They talk about the coordinate effect, some of the forces, but why? What's the intuitive understanding to the physics? There is no actual qualitative explanation to why the phenomenon works, other than some mathematical models. And also, the question also has stability to external perturbations. That was an extremely key point. There is no actual physical intuition used on why the situation. Example, a simple diagram of using torques and angular momentum to explain it. So I believe the reporter lacked the ability to fully address the statements within the problem statement and use a qualitative physics explanation.
Okay, thank you. 3 minutes time to question from the reviewer.
First, I want to ask both sides, what is the source of force of coordinate effect? Which material exert force? Which material exert the coordinate effect force?
So
Air or this and water?
Am I able to address the question?
What is the source of force of coordinate effect?
Okay, so the quantum effect is
Just give me one word. Which
it's the
material?
ambient pressure from the air pushing down.
Oh, okay. What about
Water.
Oh.
The water.
Oh, okay. You think it's the water?
Yes. That
So if you put the whole system into an environment without air, can the system still can the phenomenon still occur?
I think it will be affected by the without air will be affected the water jet.
Okay. Is the water membrane surrounding the disk completely continuous? Yes. Does in some of the parts it break?
Sorry.
Does the water membrane surrounding the disk completely continuous?
And then
Yes.
it will be stashed out of and we didn't consider this, but it will be a complete stashed out of the rotation of it.
Yes, and have you and if you assuming that the water velocity of the water membrane surrounding the disk is constant from the beginning to the
We didn't calculate that part, so we didn't.
what about the opponent things?
Sorry, repeat the question first.
Is the
Is the water fully surrounded?
is the velocity in the water membrane all the same?
No, of course not. There's a distribution of velocity as it goes across.
I have seen that in your experiment is your water jet completely vertical.
Yes, it is complete vertical.
So your disc do not turn all around the jet if you no. All right. And also, did you have a quantitative explanation why you can use such a method to explain the stability? And I have seen that in your page 33, you have simplified it into a spring system. Do you think it's rational for you to simplify it to a spring system?
I will be discussing about the proportion to the period of it, so I believe that this can be quantitatively explained that the period affected by the rate is the percentage and the weight of this.
What about
I don't think this is reasonable because there's quantities that are conserved, such as angular momentum, and they need to be taken into account, either qualitative or
okay.
quantitative.
And do you think the air jet that the airflow that you exerted on this is the only form of perturbation? Are there any other perturbations exerting at the same time?
I believe that there will be other, main part will be the airflow.
What about the Black-Rayleigh instability of the water?
So sorry.
What about the Black-Rayleigh instability, which means the air gaps in the water jet? Is this what
But that goes back to the laminar flow. As it was not laminar flow, it
Thank you very
was
much.
Okay, thank you. 2 minutes time for preparation of the review. I'm Liu from Team China. Actually, I will bring the review report of the suspended water. First, I have the problem analysis, and I think the reporter should define the stability quantitatively and define external perturbations more clearly. And this is the first part, is my report summary. First, in the problem analysis, he said that the suspended rotated. This is the correct phenomenon, and it can also include some of the external perturbations and types of investigating of the stability by simplifying the system into a spring system, which I have seen in this page. And in his theoretical analysis, he got the reacting force due to Coulomb effect. But I think his consideration is irrational because it's not by the water. The force is exerted by the Coulomb effect is exerted directly by the air. And he also used a force balance or some of the other motion equations to calculate the system. And in his experimental verification, he changed some of the variables, such as the mass of the disk by digging a hole in it and cross area. He also has some of stability measurements. This is my reporter's pros and cons. He has observed successful phenomena, and you include airflow to measure the stability of the system. And I saw that he simplifies the spring system. He also investigates. Also, his theory can explain this trend from phenomena, such as the angular velocity or the angles relationship with different parameters. He also investigates some other independent variables, such as the mass of this by digging a hole, which is, I think, it's a wise device. But there are also many problems, such as he can't explain the originality of the measurement of stability. In his experiment verification, he didn't even explain why he can use airflow to explain the phenomenon, to measure the stability. And also, he irrationally simplified the system into a spring system. And he didn't use value or the magnitude of vibration to qualify describe the stability. He also have a very important irrational consideration of the force due to Coulomb effect. Coulomb effects are exerted by air directly, not by water. And he didn't explain why, not this point. And he also irrationally neglecting the air gaps at the top of the water jet, which is the blood-to-relay instability. He also dismissed the different flow velocity at the water membrane surrounding this, which is Kelvin Helmholtz instability. And he has an irrationally simplified model, which causes a very large error. It also has an irrational consideration of the cross area, because it is not the cross area of the water jet that is influencing, but the ratio of the thickness of the disc to the cross area, to the diameter of the water jet. It is actually not the cross area of the water jet that is exerting. And then talk about the opponent. I think the opponent is very good. He got focused on very much details about flow water, point out the flow type, and point out irrational stability, and find out the factor quality of the water jet, and perturbations on different directions, especially on the third dimensional, which in this direction it is extremely not stable. But he didn't. He knows what is the principle of Coin effect, but he didn't mention it in the discussion. And yes, I have also some other important points not found. And in the discussion part, the opponent was linear, different surfaces. How do you observe external perturbations? Reporters, the reporters gave this responses, and I think that the reporter should consider more directions perturbations. And in my suggestion, I suggest to qualify the stability in investigate further into the principle of coordinate effects. Thank you.
Thank you. And there's 2 minutes time for concluding remarks by the reporter.
So this will be a remark on the reporter. So first, the sound will be developed by the positive force caused by the water jet, and also the centrifugal force that caused by the corona effect. And also, we will assume that the water will be at the same angle, and with the combined force will be, and so the combined force can be modeled by the single harmonic motion and about the stability of this. And all the perturbations will be defined by the slow displacement of the we are doing by radius by going after it. And about the perturbations that we are using the simple harmonic motions of the K constant to a proportion that will be representing the stability of it. And the weight depends on the just of the velocity of it, and also the flow rate and the radius of the flow rate of the water jet. And we have tested the parameters that will be about the radius, the jet area, and also the jet velocity. And we have tested the forces with the laminar force and turbulence that will be the same effect that comes on the disk. And we are changing the moment of inertia, that the mass will be added on the center of the thing. So I think that when it is added on the center of the method, the moment of inertia will be affected as much. About the surface of the disk, that the opponent have mentioned that the rubber surface it will be harder for the water to stay on the surface, so it will be harder to suspend it. And we'll be discussing about the stability. We are only decided in one direction, I believe. And we have tested in other experiments that when we are changing the direction of it, we have the similar result of in our direction that we put in our report. And about the relative stability and the velocity distribution of the jet will not consider in the unified model. Thank you.
Thank you. And there's 5 minutes time for the questions. So if you don't mind, I'd like to start right away. A question for the reporter. You mentioned that this was undergoing a simple harmonic motion, right? Can you clarify why this assumption is justified in your opinion?
This is the water jet and this is the disk. For example, we have the perturbation that causes that this is more closer to water jet, that the water dust around this will become smaller. So with the smaller water now, that the forces that are in this direction will be smaller, so it will cause this to be compact. And when it's too over, that it will causes the more water will be on this route. This will be causing more force that are on this direction.
Okay. Question to the opponent: do you think that is justified to?
No, I don't think it's justified. No, I don't believe it's justified, because as we've talked about, there's more than just that. There's other types of disruptions. But as the reviewer brought up, as you can see in the video, the flow is obviously not laminar flow. Something like this where the force is constantly distributed across that jet's cross-sectional area. But because it's sending in large droplets of different diameter size, you can't assume such like oscillations are the same, and it wouldn't create that linear relationship there.
Thank you.
Jacob?
Yes. So you talked about the angle that it hits and the angle where the jet leaves being the same. Do you have any experimental verification of this fact?
Actually, the water will splash about around all of the this.
Yeah, but you said these two angles were equal.
And this will be just a simplified approximation of the
Okay.
theory.
Sorry.
You talked about centripetal and centrifugal forces. Are they the same, or can you tell me what the difference is, please? Centripetal and
Centrifugal and
centrifugal
centrifugal forces.
Am I able to answer the question? It's for the reporter, I guess.
There will be a centrifugal force that causes the water will give this will give the water, and the centrifugal force that will be the water affixed to the this.
Thank you.
Okay, Morten?
Okay, I have a question for opponent. You stated that omega should be. Do you agree with the fact that omega should be constant when the ball is perturbed?
Omega is constant, depending on how you do your external perturbation. In this axis,
And could you clarify why it should be constant?
if you were to impact, say, an external perturbation from this direction, it would not affect omega in that direction, because omega is another rotation axis.
Wouldn't the jet affect the omega?
With the jet, of course, especially when you have something that is a laminar flow, the jet can't be simplified, and that would eventually affect your omega.
So you think that the fact that it's not laminar should affect the omega?
Yes, it would affect the omega, because the force used
Okay.
is rho v squared, which assumes laminar. Jacob?
Yeah. And can you show, I think it's slide 32 for the recorder. Yes. So just to clarify, so did you say that this is a proportionality in your presentation?
No, this is you have a this will have the positive relationship with the square root of a sine theta over 1. 1 over the square root of a sine theta.
Oh, okay, thank you.
No more questions, any of you?
Yeah, then,
You got one more?
yeah,
Sure.
yeah. So I have a question for the reviewer. So you mentioned that the quantum effect is caused by the air. Sorry, oh, wait, the reviewer. You mentioned that the quantum effect is caused by the air. So can you just shortly, so what is the air doing to the water jet then?
Quantum effect is here, right? But can I draw a graph or can just talk about it? It is if the water jet aiming upwards, there are some of the air surrounding it, and this is the water jet, this is the disk, and when it's at the attachment point, there will be a low pressure area between the water jet and the disk, and there's a high pressure area outside which pushes the water jet to deflect it to the surface of the disk. And yes, this is how the water surrounding the disk, and the reacting force is, this is the, at the attachment point, this is the low pressure area, but on the left side of the disk, there's a high pressure area which push the disk onto the water jet and makes it stable.
Thank you for your answer.
No more time for additional questions, and we'll move on to grading. Like with them? So first of all, we show our marks for the reporter quiz. I'll read out the marks from my site. It's 6, 5, 6, 3, and 5. Next, for the opponent please. It's 6, 7, 8, 7, 7. And for the reviewer, please, it's 5, 6, 8, 4, and 6. 1. So we have a low 3 on the report by Jacob.
Yes. So, first of all, I would like to say to the recording that I truly respect the experimental effort taken here. I mean, there's a lot of experiment, and those are your like. The problem starts on especially on your theory model. So you make this huge assumption on how the angle goes in and out without validating it. I mean, it was very, very hard to follow how we managed to construct it, but I get the feeling that it basically treats the disk as standing more or less still, and then just look at the water, sort of integrating the path around, and I disagree completely with this way of treating. What I also have a lot of problem with is in your data analysis, that, for example, you show us graphs and you say, oh, this is a proportionality, this is a, and so on, and then you show us rather some kind of linear fits instead, and I find that borderline disgenuous. I mean, you should really be, I mean, if things is a proportionality, please show us the origin, so we truly see that the line passes through. So, and in the discussion phase, I felt that the opponent brought up a lot of really valid things on how the mechanisms happen, and you couldn't really respond too much and bring too much physics to that. So again, I want to say I respect the effort carried out in doing all these experiments, but I do think that analysis is significantly lacking. Thank you.
Okay, comment on any of the high marks, 6 by Daniela.
I gave you 3.5 of
6 on the report, right? Yeah.
Yeah, on the report. Because you explained some of the important parameters. I think not very well explained, but so I give you 3.5 and for the report and 1.5 for the discussion, so 6.
Okay. Yeah, short comment on my 6 maybe. I felt like, so I'm quite surprised obviously. I felt like this clearly was an above standard report. I mean, clearly there were theoretical shortcomings, like for example the theta equals theta assumption that, as Jacob pointed out in the question phrase, was clearly unjustified, but I think the experimental effort done, as also Jacob pointed out, was clearly above standard. And so I still added 4.25 for the report. I added 1 for the discussion because I felt you didn't, so 1 out of 3 because I felt like you couldn't really answer some of the opponent's questions. And I felt like the discussion was rather weak compared to the report. And I subtracted 0.5 for jury questions finally, because as I asked for, I think the simple harmonic motion is completely unjustified. Despite that, I think the problem is one of the more complicated ones to work on, especially when it comes to investigating external perturbations. This is clearly a point you can always criticize because it's very hard to do that. And I somehow estimate your efforts in actually trying to do that because it's not easy to do it. So that's how I end up with a final mark of 6 because I still believe this was an above standard report. To the opponent, high mark of 8 by Daniela once again.
Because the opponent gave some very important questions and lead the opposition very well because he tried to so I gave you 1 point for questions because 3 points for speech and 3 points for discussion, so I gave you 8.
Okay.
I gave 7, and what I like is that you really try to focus on the missing parts of the burn, because I think, partly I'm opposing this statement, but I think that there should have been at least some qualitative discussion of the stability, and that's the thing you've tried to do during the opposition. That's why I gave you again 7, because I think that was relevant.
Mm-hmm. Yeah. Actually, so I was in a mark with a 6. I was tending between 6 and 7. So obviously 7 was the majority voted for 7. So it was a rather strong 6 compared to the report that was a rather weak 6. So in the end, it looks like the same mark. But Actually, it's not. I really liked your questions, so I added 1.25 for questions because I felt like the questions were fully relevant. The questions were aimed in clearing up the points that were basically lacking by the Woodwater's explanation. However, I felt like the opponent's presentation was was in some aspects rather superficial, in others not. So it was a mixture of pros and cons. So I added, for the opponent's presentation, I added 2 out of 4. And also for the discussion, I added 2 out of 4 because I believe that you should have rather focused more on 1 or 2 or 3 aspects rather than going along with this. So I was under the impression that you had like an idea of addressing 7, 8, 9 topics rather than sticking to one and clearly stating your own opinion. So, I mean, clearly this again was a good opposition. That's why it's still a 6, like not a 4, not a 5. But you could have easily gotten more points if the discussion was clearly structured. So this is my personal opinion. Okay, the review. Low 4 by Jacob.
Yes. So the reviewer, I think, brought up and tried to cover a wide range of topics. Some of them we found appropriate. However, to me, the key concern here is that you make a huge thing about this, about the quanda is a air pressure effect. I mean, really, what is in the center of this problem is an interaction between the water jet and the surface of the ball. That's really what this problem is about. So I have some trouble really understanding mechanistically how the air comes into all, and this you really had as your center point. Similar as well, I found that the reviewing the opposition really didn't really add too much of my way of saying for what the opponent did. So you basically said some points were missed. That really doesn't really tell me what was missed in the end. So I would like to see that. So on your so for the report, I gave you 1 for the overview of that. For the opposition, 1.5. For the discussion analysis, 0.5. Let's see if I haven't got out of sync with. Yeah, I've got out of sync myself. For questions, I gave you 1. For the report, 1.5. Opposition, 0.5. Discussion, 0.5. Miss, 0.0. And then I subtracted 0.5 for the quanda effecting.
Okay. High 8. I don't know.
Yeah, but there's some important questions about the continuity of the jet. They asked questions about the distribution of the velocity, which is important for the. And the next question was about the angle of the jet. And which is important too. So I gave 2 for questions, and 2 for the review of the report, and one for position.
Okay. Okay. So in case there is no more justification needed by any of the teams, we'll proceed to break and be back in 5 minutes. Thank you.
I have a vote on 45.